To learn about power factor and efficiency calculations, consider several resources. Books provide in-depth explanations. Power factor and reactive power control by T. She offers detailed insights. Electric Power Systems, a comprehensive introduction by J. D. Glover, Mule Cutler S. Sarma, and Thomas J. Overby presents a comprehensive overview. Electrical Power Engineering Theory and Practice by S. N. Singh covers theoretical and practical aspects. Online resources offer interactive learning experiences. The Power Factor Calculator and tutorial on Electric FOU provides a practical approach. The Power Factor PowerPoint from the University of Illinois offers a visual learning aid. Efficiency and power factor calculations on metering. Com explains the calculation processes. How to calculate power factor on Electrical Classroom offers hands-on calculations. Technical papers provide detailed analysis and practical guidance. Power Factor, a guide to measurement and improvement from National Grid offers practical advice. Improving Power Factor, a guide from Eaton provides strategies for improvement. Power Factor Correction, a practical guide from Schneider Electric offers a hands-on approach. Courses offer structured learning paths. Power Factor and Efficiency Analysis on Coursera offers a specialized curriculum. Power Factor and Reactive Power on EDX provides a structured learning experience. Power Factor Correction on Udemy provides specific training. Power factor is defined as the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. It represents how effectively electrical power is being used. An ideal power factor is 1, indicating that all supplied power is used for doing useful work. A lower power factor indicates that a significant portion of the power is reactive power, which does not perform useful work but circulates in the system, increasing current flow and losses. Power factor correction involves adding capacitors to the electrical system to offset the effects of inductive loads, thereby bringing the power factor closer to 1. This improves energy efficiency, reduces electricity costs, and increases the system's capacity. To calculate power factor, use the formula power factor equals real power divided by apparent power. Real power, measured in kilowatts, is the actual power consumed by the load. Apparent power, measured in kilovolt amps, is the product of the voltage and current in the circuit. For example, if a load consumes 100 kilowatts of real power and has an apparent power of 125 kilovolt amps, the power factor is 100 kilowatts divided by 125 kilovolt amps, which equals 0.8. Efficiency is a measure of how effectively an electrical device converts electrical energy into useful output, such as mechanical work, light, or heat. It is defined as the ratio of output power to input power, expressed as a percentage. Higher efficiency means that more of the input power is converted into useful output, with less wasted as heat or other forms of energy loss. To calculate efficiency, use the formula efficiency equals output power divided by input power multiplied by 100%. Output power is the useful power delivered by the device. Input power is the total power consumed by the device. For example, if an electric motor consumes 10 kilowatts of input power and delivers 8 kilowatts of output power, the efficiency is 8 kilowatts divided by 10 kilowatts multiplied by 100%, which equals 80%. Reactive power is the power that oscillates between the source and the load without performing any real work. It is caused by inductive loads, such as motors and transformers, and capacitive loads, such as capacitors. Inductive loads cause the current to lag behind the voltage, while capacitive loads cause the current to lead the voltage. Reactive power is measured in kilovolt amps reactive. A high level of reactive power can cause voltage drops, increased current flow, and higher energy losses in the electrical system. Apparent power is the vector sum of real power and reactive power. It represents the total power that the electrical system must supply. Apparent power is measured in kilovolt amps. The relationship between real power, reactive power, and apparent power can be represented by the power triangle, where apparent power is the hypotenuse, real power is the adjacent side, and reactive power is the opposite side. The power factor is the cosine of the angle between real power and apparent power in the power triangle. Understanding these relationships is essential for optimizing power system performance and reducing energy costs. When evaluating power factor, it is important to consider that inductive loads such as motors, transformers, and reactors consume reactive power, which causes the current to lag the voltage. Capacitive loads, such as capacitors and some electronic devices, generate reactive power, causing the current to lead the voltage. Power factor correction techniques aim to minimize the reactive power by adding capacitors to compensate for the inductive loads. This brings the power factor closer to unity, improving the efficiency of the electrical system. Poor power factor can result in several problems, including increased energy costs, reduced system capacity, voltage drops, and increased losses. Utility companies often charge penalties for low power factors because they must supply the extra reactive power. Improving the power factor can reduce these penalties and lower overall energy costs. Power factor correction can also increase the system's capacity by freeing up conductors and transformers to carry more real power. This can postpone or eliminate the need for costly upgrades to the electrical infrastructure. Voltage drops can occur when there is excessive reactive power in the system. Correcting the power factor can reduce voltage drops, improving the performance of voltage-sensitive equipment. Higher current flow due to reactive power leads to increased losses in conductors and transformers. Power factor correction reduces the current flow, thereby reducing losses and improving the overall efficiency of the electrical system. There are several methods for power factor correction, including using capacitor banks, synchronous condensers, and static VAR compensators. Capacitor banks are the most common method and are relatively inexpensive and easy to install. Synchronous condensers are rotating machines that can supply or absorb reactive power, providing dynamic power factor correction. Static VAR compensators are electronic devices that can rapidly adjust the amount of reactive power injected into the system, providing precise power factor control. The selection of the appropriate power factor correction method depends on the specific characteristics of the electrical system, including the types of loads, the level of power factor correction required, and the budget constraints. A power factor of 1 indicates perfect efficiency, meaning all the power supplied is used for useful work, and there is no reactive power. A power factor of 0 indicates that all the power is reactive power, and no useful work is being done. In practical applications, power factors typically range from 0.8 to 0.95. Many utility companies require a minimum power factor of 0.9 or higher to avoid penalties. Improving power factor can significantly reduce energy costs and improve the overall efficiency of electrical systems. When selecting capacitors for power factor correction, it is important to consider the voltage rating, capacitance, and harmonic content of the electrical system. The voltage rating of the capacitors should be equal to or greater than the system voltage to prevent failure. The capacitance should be selected to provide the appropriate amount of reactive power compensation. Harmonic filters may be required to prevent harmonic currents from damaging the capacitors. Harmonics are distortions in the voltage and current waveforms that can be caused by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause overheating, equipment failure, and inaccurate meter readings. It is important to analyze the harmonic content of the electrical system and install appropriate harmonic filters if necessary. An energy audit is a comprehensive assessment of the energy consumption of a building or facility. It identifies areas where energy is being wasted and recommends measures to reduce energy consumption. An energy audit can help identify opportunities for power factor correction and other energy efficiency improvements. The cost of power factor correction equipment can vary depending on the size and complexity of the electrical system. However, the savings in energy costs can often pay for the equipment in a relatively short period. There are also government incentives and utility rebates available to help offset the cost of power factor correction. Power factor correction is an important aspect of electrical system design and operation. By understanding the principles of power factor and implementing appropriate correction measures, it is possible to significantly reduce energy costs, improve system capacity, and enhance overall electrical system performance. Continuous monitoring of the power factor is essential to ensure that the power factor correction equipment is operating effectively and that the electrical system is performing optimally. Regular maintenance of the power factor correction equipment is also important to prevent failures and ensure long-term reliability. Power factor correction is not a one-time solution, but rather an ongoing process that requires continuous monitoring and maintenance. The benefits of power factor correction include reduced energy costs, increased system capacity, improved voltage regulation, reduced losses, and enhanced equipment life. By implementing power factor correction, businesses and organizations can save money, improve their environmental footprint, and enhance the reliability of their electrical systems. The power triangle is a graphical representation of the relationship between real power, reactive power, and apparent power in an alternating current circuit. The real power is the power actually consumed by the load and is measured in watts or kilowatts. The reactive power is the power that oscillates between the source and the load and is measured in volt-amps reactive or kilovolt-amps reactive. The apparent power is the vector sum of the real power and reactive power and is measured in volt-amps or kilovolt-amps. The power factor is the cosine of the angle between the real power and the apparent power in the power triangle. A high power factor indicates that the real power is close to the apparent power, meaning that the circuit is efficient. A low power factor indicates that the reactive power is significant compared to the real power, meaning that the circuit is inefficient. To calculate the power factor using the power triangle, divide the real power by the apparent power. The result is the cosine of the angle between the real power and the apparent power, which is the power factor. The power factor can also be calculated using the formula power factor equals real power divided by apparent power. The real power is the actual power consumed by the load, and the apparent power is the product of the voltage and current in the circuit. For example, if a load consumes 100 kilowatts of real power and has an apparent power of 125 kilovolt amps, the power factor is 100 kilowatts divided by 125 kilovolt amps, which equals 0.8. Understanding the power triangle and the power factor is essential for optimizing the performance of alternating current circuits. By improving the power factor, it is possible to reduce energy costs, increase system capacity, and improve voltage regulation. There are several methods for improving the power factor, including using capacitor banks, synchronous condensers, and static VAR compensators. Capacitor banks are the most common method and are relatively inexpensive and easy to install. Synchronous condensers are rotating machines that can supply or absorb reactive power, providing dynamic power factor correction. Static VAR compensators are electronic devices that can rapidly adjust the amount of reactive power injected into the system, providing precise power factor control. The selection of the appropriate power factor correction method depends on the specific characteristics of the electrical system, including the types of loads, the level of power factor correction required, and the budget constraints. Power factor correction is an important aspect of electrical system design and operation. By understanding the principles of power factor and implementing appropriate correction measures, it is possible to significantly reduce energy costs, improve system capacity, and enhance overall electrical system performance. The NEC, or National Electrical Code, provides guidelines for electrical installations to ensure safety. While the NEC does not explicitly mandate power factor correction in all cases, it does address the importance of efficient energy use and the impact of power factor on system capacity. NEC Section 220.87 provides guidance on calculating the demand load for non-dwelling units, which can be affected by power factor. If the power factor is low, the apparent power, measured in kilovolt amps, will be higher than the real power, measured in kilowatts, requiring larger conductors and overcurrent protection devices. NEC Section 310.15 addresses conductor ampacity and the need to adjust ampacity for factors such as ambient temperature and the number of conductors in a raceway. A low power factor can increase the current in the conductors, requiring a derivation of the conductor ampacity to prevent overheating. NEC Section 430 covers motors and motor circuits. Motors are typically inductive loads that contribute to a low power factor. The NEC requires that motor circuits be sized based on the motor's full load current, which is affected by the power factor. Improving the power factor of motor circuits can reduce the current and allow for smaller conductors and overcurrent protection devices. NEC Article 460 specifically addresses capacitors. This article provides requirements for the installation, protection, and control of capacitors used for power factor correction. It includes guidelines for capacitor sizing, overcurrent protection, and disconnecting means. In general, adhering to NEC guidelines helps ensure that electrical installations are safe and efficient. While the NEC does not always mandate power factor correction, it does provide requirements that indirectly address the impact of power factor on system capacity and conductor sizing. Improving power factor can help reduce energy costs, increase system capacity, and improve overall system performance, while also complying with NEC requirements. When performing power factor calculations, it is important to use accurate measurements of voltage, current, and power. Power analyzers and power quality meters can be used to measure these parameters and calculate the power factor. These instruments can also measure harmonic distortion, which can affect the accuracy of power factor calculations. It is also important to consider the diversity factor of the electrical system. The diversity factor is the ratio of the maximum demand of a group of loads to the sum of the individual maximum demands. If the diversity factor is less than 1, the power factor correction equipment can be sized based on the maximum demand of the group of loads, rather than the sum of the individual maximum demands. This can reduce the cost of the power factor correction equipment. Power factor correction can also improve the stability of the electrical system. A low power factor can cause voltage fluctuations and instability, which can affect the performance of sensitive equipment. Improving the power factor can reduce voltage fluctuations and improve system stability. Power factor correction can also reduce the risk of equipment failure. A low power factor can cause overheating of transformers and conductors, which can lead to premature failure. Improving the power factor can reduce the current flow and temperature, thereby extending the life of the equipment. When designing power factor correction systems, it is important to consider the long-term reliability and maintenance requirements of the equipment. Capacitors have a limited lifespan and may need to be replaced periodically. It is also important to ensure that the power factor correction equipment is properly protected from overcurrent and overvoltage conditions. Power factor correction is an important aspect of sustainable energy management. By reducing energy consumption and improving system efficiency, power factor correction can help reduce greenhouse gas emissions and promote a more sustainable energy future. Implementing power factor correction can also enhance a company's corporate social responsibility and improve its public image. Many companies are now incorporating sustainability into their business strategies, and power factor correction is a valuable tool for achieving these goals. In summary, studying power factor and efficiency calculation involves understanding key concepts, utilizing appropriate formulas, and considering the practical implications for electrical systems. Resources such as books, online tutorials, technical papers, and courses can provide valuable knowledge and skills in this area. By improving power factor and efficiency, it is possible to reduce energy costs, increase system capacity, and promote a more sustainable energy future.